Today we're gonna look at the fast pulse generator, and we're gonna test some oscilloscopes, very cheap oscilloscope, handheld oscilloscopes, and we'll see if they actually deliver the bandwidth that they claim they do. So a little bit about this pulse generator. I built it probably 10 years ago, based on ADCMP 580 chip. It's basically a very fast comparator. It can generate, it basically can get a pulse in, and the pulse out is 37 picoseconds, typical rise time. So it's good for measuring bandwidth of an oscilloscope. So the formula for measuring the bandwidth on oscilloscope would be something like 0.35 or 40 for modern oscilloscope, and you divide that by the rise time. You can get the rise time in if you get the rise time in microseconds, then the bandwidth will be in megahertz. So basically I have this we'll start with this tablet oscilloscope. So it has a nice touch interface. They claim it has 100 megahertz and 1 gigasamples per second. I wasn't able to get that, so first of all, it doesn't always. So if I increase the time base to 10 nanoseconds per division, it doesn't always trigger. So it's already having, so at 50 nanoseconds per division it triggers well, but at 10 nanoseconds it doesn't trigger well. I'm gonna try to catch one of the, so one of the pulses. Again, this is I played with this. This is not super normal. Maybe I'm doing something wrong. Anyways, let's see if I can catch one of the pulses. So playing, maybe we can play over trigger here. Not getting the pulse. So anyways, you can see quickly here maybe. So this is at 15 nanoseconds per division. I was able to previously catch a pulse. So let's play with coupling here. Let's go to a C coupling. I have a 50 ohm terminator here. It's doing something very weird at this stage, so it definitely doesn't function very reliable at these frequencies. So anyways, if we try to do the rise time, let's try it here, then we get around 15 nanoseconds. Let's say at 10 nanoseconds, let's round it, 15 nanoseconds. So this bandwidth, if you divide 0.35 by 15 nanoseconds, that's going to give you between 20 and 30 megahertz. So no way this is delivering 100 megahertz. So is this oscilloscope good? Yeah, maybe if you don't mind not getting the entire frequency. It doesn't really work well at high frequencies. So let's look at another one. because they're not well bad. So this is hanmatek ho52. I'll try to connect it one hand. Okay, so this is pause now. Let's try auto set, see what it does. So, okay, so we got the pulse. I'm gonna try. We got the pulse. It's 1 kilohertz coming from my signal generator. I also have the input signal on this oscilloscope, so this goes into the signal generator, and basically there's a comparator here and a very high rise pulse, which is like probably a couple of order of magnitudes higher than what we're trying to measure, goes into this oscilloscope. And I have a 50 ohm terminator because I'm not sure if this oscilloscope can terminate on their own. So anyway, let's see the rise time here. We're gonna go to horizontal menu. We're gonna raise the time base. Actually, it's the other way around. So we're gonna start seeing. Okay, so the limit reached. I'm gonna pause it. Gonna go to my cursor, measure, cursor. Okay, so we get 3.6 nanoseconds. So 0.35 divided by 3.6 nanoseconds, it gives us around 100 megahertz bandwidth on a single channel. Now if I enable another channel, let's try doing that. Okay, let's run. Oh, okay, so you see we're getting half a bandwidth. So in conclusion, this oscilloscope, this cheap oscilloscope, are hit and miss. Make sure you measure the bandwidth when you get. You can build such fast pulse generator in a simpler way, or you can get some other generator. Anyways, hope this helps. So thank you for watching.